Hey, good afternoon, everyone. So we've got our midterm next Monday, and I put a list of topics up on this slide. I think I got them all, but basically it'll be everything we covered so far in the course. You've got the 3 quizzes that you can that you'll be able to review, and then on Monday, next Monday, you can optionally come to class, and I will do a review for the exam. The exam will be online. It will be given through Moodle, and you'll have all week to take it. So you can take it any day next week that you want. Yes?
So when does it open up, and when does it end?
It'll open up Monday, I think Monday at midnight, and then I'll have it end on Friday at midnight. And you'll have 75 minutes to take it once you start taking it, and there'll just be one attempt. So, so if you want to come to the review, obviously you want to take it after class on Monday. Yes?
What is the format and how many questions are there?
It'll just be multiple choice, like the quizzes. It'll the same format as the quizzes. The number of questions, depending on the makeup, it'll probably have 15 to 20 questions. Okay? Because 15 questions, it's 5 minutes. 5 minutes a question. Okay, so the topics are, these are not in any particular order, but we covered the RISC ISA. So I'll have questions on there where you have to write or analyze snippets of code or translate between C and RISC-V. But make sure you understand the R, I, U, B, and J types. I'm going to cover the B and J types today. So I haven't talked about these yet. I've only talked about R, I, and U so far. And then control hazards, I'll talk about that today. And then I covered microarchitecture, which are when you have the block diagram of the CPU and you've got muxes and enables, and for a given instruction you have to set your control signals up. So that's similar to the types of questions I asked on quiz 3. Then I covered fixed point arithmetic. Make sure you remember how that works. Then I talked about logic circuits in general, combinational versus sequential, and what that means, as well as logic values. So remember that you can have 0 or 1, but there's other values like high impedance or don't care, unknown, uninitialized, that kind of stuff, double-driven, conflict. Then hardware description language, simulation versus synthesis, and behavioral versus structural. And then I covered most of the time we spent on system Verilog, and I've done that. The reason I've spent so much time on system Verilog is I wanted to try to get through this so we can get you started in the labs as soon as possible. Once I finish this lecture on branch and jump instructions, then I'll be transitioning into more conceptual topics for the course. We'll switch into more of a theory mode rather than an applied mode. Most of the stuff we talked about in class was designed to get you going in the lab, so it was very applied. So for system Verilog, I talked about how to read a simulation waveform. And then there was modules and structure. Structure is the idea of when you instance a module, you have a hierarchy, and signals have different names depending on where you're looking at them in the hierarchy. And there's inputs and output ports and how you connect them. Continuous assignment is just the assign statement and the implications of that. Each assign statement, you can't double drive the same signal with 2 assign statements. Assign statements are triggered on any signal that appears on the right-hand side, and the ordering of them, the assignment statement doesn't matter, right, in the code. And then numbers, where you can define a number, you can give it a bit width and a base. Bit manipulation, where you can concatenate bits and slice out bits and duplicate bits. Reduction is when you have an operator that can take several bits and reduce them down to 1 bit, like through a big, AND gate, for instance. Always statement, we talked about. There's the always comb and the always underscore FF, and then just the always. So we talked about 3 types of always statements. There's actually more than that. But I mentioned that the always underscore FF is for registers in RAM and sequential logic in general. Then there's the always com, which is for combinational logic. And then we also talked about just always. You have to be careful with the one that's just always, though. That's intended only for test benches. Now, you might have noticed, there's also a form where you say always, and then at, and then sensitivity list. This is the original always statement from just plain old Verilog. System Verilog introduced the underscore FF and the underscore com and the underscore latch, and there might even be more. These are System Verilog additions. The reason why we use these System Verilog variants is because it provides for error checking. If you put an always com and you accidentally have memory in there, because that can happen if you forget to assign something, then ideally the compiler would catch that and throw an error, although I found that ModelSim doesn't always do that, but Quartus will, right? So these are designed to protect you, essentially, but you don't need to use these. You could just use a plain old always with an at and a sensitivity list. So in the old days of Verilog, if you wanted to do combinational logic, you would say always at star, right? And that was equivalent to saying always underscore com. You guys with me?
Yeah.
Okay, so just to clarify that, you'll probably see the always at star. If you ever look at any legacy Verilog code, you'll see always at star. And you might be confused. But again, these are System Verilog extensions. Okay, so then we talked about sensitivity lists. Sensitivity lists with always underscore com are implied. It's just based on the context, how you write the code. The compiler figures out what the sensitivity list is. Any signal treated like an input is in the sensitivity list. But if you say always underscore FF, and of course then you have the at sign, you have to explicitly give the sensitivity list, right? And again, the sensitivity list is just anything that changes in there activates the always statement and updates the outputs. Default assignments are used whenever you have an if statement inside an always statement, because default statements are just when you basically assign all the outputs up at the top of the always statement, and then you can have some like if statements underneath there. And the default statements just make sure that you assign all the outputs. Now this is important in this class because when you make your control unit, a lot of the control signals, like you might have noticed when we were going over the control signals, let me skip ahead here a bit. You might have noticed that when we went through these examples, a lot of these things are kind of the same. Like ALU source is almost always 0, and reg write is almost always 1, and GPU I/O write enable is almost always 0 because it's only 1 under one specific instruction, that CSSRW whatever instruction, right? So a lot of these are pretty much always the same. And so when you make your control unit, you can use default assignment. Just assign all of these like signals that are almost always the same value. Just assign them right at the top of your control unit, and then underneath there you can just have all your if statements for the special cases, right? So that way you can set this guy to be 0, and the only time you have to set it to 1 is if you happen to get a CSSRW instruction, right? You guys with me? So that's the defaults are very useful for that. And it also ensures that you don't get a latch, that you don't have a path. You don't want there to be a path in the always that doesn't assign something, because then the compiler will have to put memory in there for that. Because if you don't assign an output of an always statement, it's assumed that it should retain whatever the old output was. And in order to implement that in hardware, you need a latch. Okay. Case statement is just basically like a switch statement. I think everyone was okay with that. Not very common to use a case statement in Verilog. Sequential logic was the RAM and the registers. Anything with anything with memory or that's synchronous to the clock. Sequential logic, blocking versus non-blocking assignment. That was the kind of confusing. That confuses me still. That blocking versus non-blocking. Essentially, blocking is when you have an equal sign and it enforces sequential semantics inside the always statement. Meaning, if you assign something and then you subsequently read it, you're seeing the new value, right? Whereas a Non-blocking is the less than equal to sign, and it's basically just updates the signal at the end after the always statement finishes. So anytime you read a value after having done a non-blocking assignment, the value you read is the old value. It doesn't see updates yet, right? So it's kind of it's non-blocking as a way to defer updates to an output in an always, essentially. Now, there's more to it than that when you have multiple always that look at the same inputs, but the way I described it is essentially how those two assignments are treated within the context of one always block. And then registers and RAMs and test benches. I think that's pretty much everything we've covered so far. Okay, so quiz 3 just had 5 questions on it. I'll go over that real quick. So this was one of those questions that asks you to define what the control signals are for a given instruction. But there's not just one instruction, because it's a pipeline processor with 3 stages. So there's actually always going to be, in a pipeline processor, there's going to be multiple instructions in the pipeline at different stages of execution. So in this example, we've got a multiply that's being fetched while we're executing an LUI and we're writing back an XORi. And this is important because these signals have different suffixes that relate each of these control signals to the instruction in that stage. So I ask for Reg Write WB, ALU Source EX, and Reg Select WB. So in order to solve this, you have to look at, Reg Write WB is basically what I'm asking you there is, does the instruction in the write back stage write a register, right? And the the XORi does, so that would be a 1. And then the Reg Select, ALU Source EX is asking for the instruction that's in the EX stage, what is its ALU source? Is it a register or an immediate? Well, we've got an LUI in decode. But the LUI doesn't do anything with the ALU at all. It just ignores, it doesn't use the ALU. And the reason, you might say, well, how does that determine? Well, it's okay, so the ALU has an output that potentially may just get blocked by this mux, right? So if this mux doesn't read the output of the ALU, then the ALU is essentially not being used. It's not being used to generate meaningful data, right? It's just being ignored. So so you can have a don't care for that, for the ALU source. So this is the ALU source mux, and it's actually shown here with more detail. Here it's just, it's not really, you don't really see what's going on here. There's just a kind of a placeholder. But over in this diagram, it shows with more detail what's going on in here. And so this is selecting between the, it's saying, what do you want, what's the ALU want as input B? Register or immediate? Well, the LUI does have an immediate field, but we don't stick it in the ALU. We just stick it directly back in the register file. So that's a don't care. And then Reg Select write back is this mux? This mux. This mux is selecting what goes back in the register file. Now this is hard to figure out because notice how this line feeds back. It's this ridiculously long, comically long wire that you have to trace back. And the reason for that is because the data flows kind of from left to right, but then when you write back, see, the register file is used for the decode and the write back. And so the write back's the last step, but the decode is like one of the first steps. So the reg file is typically going to be on the left-hand side of your diagram, but then the write back part is got this wraparound link to go back to the reg file. So that's why I didn't do this just to, I know it's kind of hard to figure this out with this long wire, but that's the reason why it's drawn like that. But anyway, Reg Select is saying, what are you going to write back? You got 3 choices. You can take GPIO, basically your switch values on the DE2 board, right? LUI value, upper immediate thing, shifted whatever, right? Immediate value from the instruction, or ALU result. Now, if we were doing a data memory, and you were doing a load instruction, then there would have to be an option for the load, right? Loading from memory here as well, right? Because when you load, you stick a value from memory in the register file. But we're not doing loads, so we only have these three options. So, okay, sorry. So what was I? Right, write back. What's in write back? Write back, write back. Right. Okay, so reg select write back. Write back is X or I. So what are we supposed to be writing back? Well, the X or I is writing back the ALU result, right? So.
I think you're read select, not reg write.
Oh, sorry, reg select. Yeah, sorry. Thank you. I said that wrong. Reg select. Reg write is whether we write to the register. Right. Reg select. Thank you. Reg select. So what are we reg selecting if X or I is in write back? And again, the reason why we're looking at the write back, the X or I, is because I asked for write back. I could have also asked you for reg write EX, which would then have referred to the LUI instruction. But because I'm asking about I just chose these three signals here kind of from random, right? These three, because I didn't want you to fill out a whole table. So I just chose these three. So reg write back is going to be referring to the X or I, and the X or I is writing back data from the ALU, which means that its reg select must have been 2. So that should be a 2, 1, 0, right? Okay, so then here's another question, very similar. In this case, reg write write back is referring to the instruction in the write back stage, which is LUI, and of course, yes, that writes a register, so reg write should be 1 for that. ALU source EX is referring to the multiply now. So the multiply, well, that just multiplies two values from the register file. So that should be whatever it needs to be to get a register, which is a 0, is this input here, right? ALU source should be a 0 for the multiply, because the multiply, it doesn't use an immediate, it uses two registers, RS and RS1. And then reg select, write back, is referring to the LUI, which is in the write back stage. And what are we writing back with LUI? Bless you. Reg select is this guy, and this is going to be number 1, right? Yeah, which again, this is also, this wire is kind of asinine, but it's the upper bits of the instruction shifted. So it's kind of like the 20 bits move to the left-hand side, and then that comes in into here, which means that we want to route that, we'll want number 1 for this, right? Right, now if I had have asked you for reg select EX, then it would have been whatever reg select needs to be for the multiply, right, which would have not been 1, it would have been 2, right, because the multiply takes this path, right, whereas the LUI takes this path, right? So really what this comes down to is following, well, there's two things you have to know to solve these problems. The first is what these instructions do. You have to have a good understanding of what these instructions are doing, how they work. Are they reading 2 registers, or 1 register intermediate, or is it an I/O instruction? So you have to understand that. And then you have to be able to understand how to establish these data paths, right? And also you have to understand too that you've got 3 instructions going on at one time in here because of the pipeline, right? So those are the 3 concepts here, right? Instruction behavior, which is kind of the ISA, the RISC-V stuff, Mux stuff, which is understanding digital logic, and then the pipelining stuff, which is this idea of concurrency, parallelism, instruction level parallelism. So there's a lot of stuff that comes together, but this is the kind of the main emphasis of this class is combining together your 211 and 212 knowledge. Yes?
When would we look at the fetch stage?
Yeah, the fetch stage is almost, is not much going on there. It's just the PC is getting added by 1, incremented by 1. By the way, I don't know if I mentioned this, but the program, I mentioned 1. You might remember from 212 that the PC increments by 4, right? The reason for that is because in this class we use a word addressed instruction memory. So because we don't want to multiply everything by 4. You know, the branch targets, you got to multiply those by 4, and the jump targets. We simplify things in this course by having the RAM, the instruction RAM, being 32 bits wide. So that way, if you increment it by 1, you go to the next 32 bits or the next instruction. But yeah, the fetch stage. Do you select in the next PC in the fetch? No, there's not much going on in fetch. It's really kind of simple. It's pretty much just reading an instruction. So I don't think there's any control signals for that, except for stall, I think, which I'll talk about soon. There's a stall signal, I think. Okay. Okay, how many cycles are required to perform a write to a synchronous RAM? 1. Synchronous is as opposed to asynchronous. So the register file here is an asynchronous, has an asynchronous read, which means that and actually I'm not, oh, here it is. I'm actually not showing, in this picture, I'm not showing the read ports on the register file. I didn't, like I was trying to reduce, control the amount of clutter here. But the register file has a write port, which is shown with this, the destination is plugged in here, and the data, the write data is plugged in here, right? So I show the write port. I don't show the read ports in here because the read ports are pretty brain dead. It's just the RS field, sorry, the RS1 field and the RS2 field from the instruction go directly into the ports, the address ports, read address 1 and 2, right? And luckily, with RISC, I guess with MIPS too, though, really. Yeah, MIPS had the same thing. There was no mux there. There was no control signals. Just take those fields and put them in, right? So there's not much to see. There's no control logic there. But if the register file were a synchronous RAM, then you wouldn't get the registers until the instruction goes into the write back stage, right? You wouldn't even have the source registers. You would need a cycle to read the source registers, right? And we don't want that. We want to be able to read the source registers, stick them in the ALU, do whatever you have to do in the ALU, all inside of one cycle. And that's why we use an asynchronous RAM for the reg file. But the fetch stage is a whole stage specifically because the instruction memory is synchronous. So it takes a whole cycle. So you put the PC value into the instruction memory and you'll get the corresponding instruction out in the next cycle. And that's why we have a whole stage for fetch. It's just because the instruction memory has synchronous read and this guy has an asynchronous read, right? So that's important to understand that the timing there, right? Depending on how long it takes to get the value out.
How many cycles it would be to read the value from Reg File if it was synchronous?
If this was synchronous, you'd have to have at least a 4-stage pipeline because you'd need to fetch, then the second stage would be a decode where you get the register values out. And then the next stage, you'd plug them in the ALU to do the execute. And then the 4th stage would be write back, right? And you need a cycle for that. So, yeah, and then the problem with it is if we did it that way, you might say, why don't we do it that way? Well, why not make them synchronous? The reason is because then you'd have a data dependency issue, because if you had an instruction that writes a register and then right after that you have an instruction that reads a register, you'd have to create a forwarding path for that. Right, see, this also avoids having you might remember from, hopefully you guys covered that in 212, data forwarding, right? We don't have to forward data. If we do end up with a write, if we have a read that comes after a write, then that's handled through the register file bypass logic that we put in. But the bypass logic wouldn't be good enough if we had a synchronous read on this guy. We'd have to actually put a way to take the data that was decoded out of the execute stage, out of the write back stage and put it into the execute stage, right? So that was the reason why we did it this way, to simplify. This is designed for you guys. Now the cost of that, though, that there is a trade-off. If we had done this as synchronous register file, we might have been able to achieve a higher clock speed, right? We're taking a bit of a penalty here by putting so much in that one stage. Okay. Okay, what's the result from performing a RISC mul H instruction on input values 1111, 1, and 0001, assuming the registers are 4-bit wide? So the idea here is that if we're doing a mul signed multiply, then this is a -1, and that's a 1. So we multiply -1 times +1, the result is -1, right? -1 is all 1. So the high part of that would be all 1s, right? Would be the signed bit. But if it's unsigned, if we had done a mul H unsigned, then we're now multiplying 15 times 1, which is just 15, in which case the upper 4 bits would all be zeros, right? So this problem illustrates the difference why you have to have a unsigned mul H versus a signed mul H. Yes?
Can you please, in the questions like this, add someone that we are dealing with signed values? Because I thought it's unsigned, it's just 15, and 15 multiplied 1 will be 15. So I pick 4B0000 because there's nowhere stated that it is actually signed.
Well, yeah, I mean, except like the mul, I gave you the mnemonic. I mean, if you had like looked that up, it would have said signed. But you're right, that's a good point. It would have been more clear, I think, if I had said that. But I was kind of testing your to see if you remembered that there was a mul H and a mul HU. But you're right. I mean, that was kind of, it was a little vague. Okay, so then last time, where were we? Okay, so last time, just to quickly review, I mentioned that we're trying to execute these 20, we want to implement initially 22 RISC instructions, and then we're going to add some more after this. But in lab 3, we're implementing these 22 instructions. They're all R-type and I-type except for LUI, which is the only U-type instruction. And so I've got those formats are here: R-type, I-type, U-type. These are so far so good. Really, the only thing that's weird about these, in my opinion, is this Func3 and Func7 fields. But you know, the objective here is to keep RS has to be in a consistent spot, RD is a consistent spot. Although if you have a U-type, there's no RS, right? Because it's LUI, so there's just an immediate and a destination. So, yeah.
I kind of did notice a slight pattern with some of the Func3 and Func7 ones. Opcode will always remain the same. It's just for the different, what just denotes what the R, I, U, J, B instructions are. And then the Func3 just denotes like a certain function in a I guess in a family. And because I kind of looked at them and I saw like how each function would be that had a corresponding like I type or whatever would have the exact same field or something similar. And it was kind of weird. And I looked at it, and I think there was some sort of pattern to it. I know there's a pattern to it. I'm just trying to puzzle it together just a little bit, because I know Func7, some values have the exact same value. Like one, I think like a few values they'll have zeros, or they'll just be like 1 or 20 in hex. So.
Yeah, I always assume there were. I never figured it out, but yeah, I assume there's one. But it's funny you mentioned the opcode being the same, because there's 7 bits, right?
Yeah.
So if a lot of the opcodes are the same, it seems like you're wasting a lot of bits, right? You got 128 possible combinations here. But I think that said, I think the reason they do that is because there's a 16-bit version of the RISC-V instruction set. And I think the reason the opcode is so big might be to accommodate the 16-bit version, which we don't use in this class. But there's a compressed, they copied that from ARM. ARM has something called the thumb instruction set. It's for really super lightweight processors. So that might be the reason why you're seeing a lot of the same opcode, which seems wasteful. Because, like I said, those bits might be reserved for the smaller instructions. I don't know. I'm just guessing. I never looked. Okay, then we talked about the is this right? CSRRW? Yeah, oh, okay, right. I always get that. Is it CSSRW or CSRR? I guess CSRRW. Yeah, CSRRW. So this is our I/O instruction. This one is control status read and write. Control and status read and write, sorry. This control and status register read and write. So this is our I/O. This is how we get data in and out of our CPU. So I talked about how in this class we are associating register CSR0 with the switches and the CSR2 with the hex. Okay, hex displays. So same instruction for input and output, which is kind of confusing, right? But the difference, you're like, well, how's my CPU going to know if I'm doing input or output? Well, it's going to decide based on the immediate, right? The CSR value. Okay. So the top level design will have the CPU, the instruction memory, which I mentioned is a synchronous RAM, and the decoders that you've already built. We try to incorporate as much of the previous work you've done into the labs. And then there's the 3 instruction stages I mentioned, and we just picked this arbitrary. Like as a designer, you guys will generally are going to have the flexibility when you design your hardware to decide how many stages, right? Like you can choose a latency, how long it takes for one instruction to make it through the pipeline. And then if you have a deeper pipeline, that usually you get a higher clock rate from that. So we just chose 3 stages just to make it kind of simple. Hopefully you remember in 212 that we talked about a 5-stage pipeline. So we wanted the instruction memory to be synchronous. Now you might be thinking, wait a second. If you initialize the instruction, you said that you initialize the instruction memory when you synthesize your design, and you can't change it until you resynthesize your design. So that's not really a RAM, that's a ROM. It's a read-only memory. Effectively, I mean, once the design is deployed on the FPGA, it's a ROM. So why do you care if it's synchronous if it's just a ROM? Well, because this way we have the option of making it programmable after the fact. You can put a RAM in there that you can actually program using JTAG after you configure the FPGA using a tool in Quartus called the In-System Memory Content Editor. Gives you the option of doing that. If you don't make it this way, like if you made it a synchronous read and you just assumed it was a ROM, then you would lose that ability to program. You guys see what I'm saying? Like, you might not have done this yet, so you might not be aware, but when you synthesize your design, it takes a long time, right? And if you wanted to be able to reprogram your CPU fast, then you wouldn't want to have to resynthesize every time you reprogram, right? You'd want to be able to just go in and put the software in, right? Change the software without changing the hardware is what I'm talking about, right? So anyway, that's what the fetch is. And then we used to have a memory stage. We don't do it anymore. And that was the reason why essentially we have that second cycle is really for the memory stage. And then the write back is its own. Okay, so those are the 3 stages. And then we talked about the microarchitecture. So here's the reg file. This is the thing I just got done telling you that I didn't show you this on the quiz. This is kind of the missing. I think I take the whole RISC and put it in 3 block diagrams, which is pretty impressive when you think about it. It's like I have 3 PowerPoint slides that show the design of an entire CPU that's Turing complete. That's pretty. I think it's pretty neat. It's pretty simple. But this shows the reg file has the bits that go into the read data 1, read data 2. This is just the 2 input registers that you want to read from. Now, I mentioned that when I did this design, I just used bit slicing, everywhere. Charles came up with an idea where you could create a way to rename all those signals without it doesn't cost anything in hardware either to do it. He called it the decoder. I don't like that name because decoder usually means something different in hardware. In architecture, usually the instruction decode is when you take the instruction and you take the encoded machine instruction and you decode it into control signals, right? Whereas he calls it decoder, he's just renaming these things, right? So the terminology is a little bit of a misnomer, but the point is that if you put this in and you rename these signals, give them names, it doesn't cost anything. You're not paying for this. It doesn't cost any hardware. It's just renaming it in the Verilog. Okay. So anyway, by doing that, you can use more sensible names. And these names don't have to cover exclusive bit ranges, right? So for example, RS1, right, is actually part of immediate 20, right? If you remember if you go back, see RS1 is part of immediate 20, right? So immediate 20 contains RS1 as well as Func3, right? But it has more bits, right? So even though this bit field subsumes these two, it's okay. You can still have these names. You can establish these namings. Okay, so but that's up to you how you want to handle that. And then we talked about how to initialize the instruction memory. And and by the way, this is the fetch stage. We essentially give it to you right here. So you can see that the fetch stage, really the only input to the fetch stage is reset, right? Which is not an official control signal, right? Because normally clock and reset we don't show in these diagrams. It's just assumed to always be there. You always have a reset, you always have a clock. So you don't have to show it in these abstracted, design view block diagrams. But yeah, so the reset, and it doesn't come from the control unit. The reset comes from the button on the DE2. Button 0, key 0. Key 0 is the rightmost button. So yeah, so that's pretty much it. I mean, that's literally, it's 2 lines of code essentially. It just takes instruction mem of PC fetch, throws it out on the instruction bus, and then, or the instruction register, whatever you want to call it, and then PC fetch gets incremented by 1. Notice that PC fetch is the only signal currently that ends with _fetch, and it gets incremented by 1, and it's 12 bits, which means we have a capacity to store 4,096 instructions. Although you can, obviously you can up that if you needed to. We have about 64 no, actually these FPGAs I think have about 128 kilobytes of RAM in total, although as I mentioned this is technically a ROM, so I don't know. I think it actually ends up implementing this with LUTs instead of RAMs, but anyway, obviously there's a limited capacity and we just used 4,096 for this lab. You guys with me? Make sense? Okay, so one thing I want to mention here, I didn't mention this last time, but this is going to become relevant for the control instructions. This PC fetch is, at any point in time, it's the address of the instruction being fetched, right? Now, the problem is that if you have to use the PC for anything in the execute stage, you can refer to PC fetch, but you should be aware that if I'm in execute and I reference PC fetch, I am referencing the address of the instruction that came after me in the program, right? Now, I can delay PC fetch, I can plug it into a register, and I can have a new signal called PCEX, which is the program counter associated with the instruction in the execute stage. That's my address. So if I'm in execute, PCEX is my address, PC fetch is the next address. Yes?
This can be used for jump instructions?
Yeah, exactly. Yeah, so there is a distinction there. I just wanted to, I'll come back to that in a minute. Okay, so we've got the EX and WB stage kind of mixed in a little bit here, kind of a soup of wires, rat's nest of wires. But yeah, pretty much just delay everything that needs to be pushed into the, go to the execute, to the write back. These are pipeline registers. This is not as clean as the diagrams you have in the Hennessy and Patterson book, this one, because I made it. But I mean, also, it's meant to be a direct, you can directly translate this into Verilog. By the way, in this class, we used to use a tool back a long time ago. It's been a while now. It's been almost 10 years. But we used to use a tool called Fpga Advantage, where instead of writing the HDL code, you would literally just draw diagrams like this, and it would convert these into code for you. It was a little easier that way. And we use that for years. In fact, I used that all the way through grad school too. And it was great, except it had some drawbacks. The first one was if you got an error, like if the compiler spit an error at you, it'd give you a line number. And you're like, I don't know what the line numbers are. I drew pictures. What line numbers are you talking about, right? Like, so that was a little weird. You had to look at generated code to figure out where the errors were. And also, I found out after I started working with companies that no one uses these graphical tools in industry, at least in my experience. Everyone writes code in a text editor, Verilog. Right? Even though they may use a graphical like this as a design and they translate it to text. Yes?
I think graphical designs are useful when you only on the early stages when you are trying to plug in, plug out different things and play with them around. But then it goes to actual implementation, code give you much more flexibility to write the things in in software.
Yeah. Like the diagrams look pretty, and it's better to have CAD designs. But yeah, it's kind of a pain. Like when you get really complicated here, you have to route wires yourself. It's a pain. It's much faster to just write text, but there is a trade-off. Obviously, it seems weird. Like, wait a minute, you're giving us a design in a graphical format, and you want us to translate it to text when there already are tools out there that allow us to just directly take this and plug it into the FPGA. Yeah, but it's more important that you understand how the actual text, because ultimately, even if you use a graphical design entry, it still goes to the text. It just gets auto-generated. Okay. Anyway, so that's just a little background information. Okay, then we went through some examples very similar to the quiz. Just make sure you're clear on this. I'm going to just kind of go through this fast because I went through this all last time. If anyone has any questions, though, let me know. This is the full control unit from the previous three examples, but obviously this is not the full set of instructions, right? There's 22 instructions, and this is less than 22 rows in this table. So this is just a starting point for you. But there's enough information in these slides to actually build a functional RISC processor with these instructions, and then once you have the stuff in your code that I've got in the slides, then all that's left for you to do is just add additional rows of this table. That's it, right, to get the rest of the instructions done. Okay, so then I mentioned, now this is the part I kind of left off with. I very quickly last time mentioned that we're giving you this test program. This is, you might say, come on, what's the big deal? It's just, you just put every instruction in once, right? Yeah, but it is nice though to have actual values that you can check, right? So the idea is that you should be able to take this program and run it on your CPU, and now you might think, okay, I run it, now what? Like what am I looking for here? I run it in Model Sim, and you got a bunch of waves. What do you do with it? You look at the register file contents. Remember, I showed you guys an example in class where I had a RAM and I blew the RAM out on the timing diagram. So what you're looking for is these values to come up. Now, obviously, they don't come up at the same time because it takes time for these guys to go in. So what you should see is register 1 should get written first with a 12, and then a cycle later you should see a 17 in register 2, and then a cycle later you'll see a 29, right? Or 1D in hex, depending on whether you're showing them in hex or decimal, right? Now, usually what happens is you'll get about partway through this, and then it's just dead, right? Or you may not see anything come up in your register file. If that happens, there's a few basic checks you want to check. Make sure you got your clock, because sometimes your test bench might not be generating a clock, or maybe you forgot to connect the clock, or maybe you have a different name for the clock and it got disconnected because you didn't have matching names. You want to make sure that you've got reset. Yeah, you should have a reset pulse at the beginning, because otherwise your program counter will start out as X's and it'll just stay as X's, because if you have X's and you add 1 to an X, you get an X. So yeah, that's a good point. Reset. Make sure you have an instruction stream coming out of your fetch stage. So you should have a sequence of instructions. Now, I don't have the machine instructions on here, but if you put this in RARs and you assemble it, you'll see in RARs you'll have a column for that. So that column will show you the sequence of machine instructions you should be getting out, right? The sequence of 32-bit values. So it's nice. Now, is it possible that you might still have a bug in your hardware even if this thing works? Yeah, because it doesn't. It's not a very exhaustive test. It tests every instruction once, but only with certain inputs, right? So, okay, all right. So for the next program, we want to do binary to decimal conversion. We didn't do this yet. Oh no, we did the square root. Yeah, sorry. Yeah. So first program that you're going to write, or the next program you're going to write by yourself. Obviously, test this in RARs because you don't want to have to diagnose hardware and software problems at the same time in ModelSim. That's awful. That's terrible. I would not. Make sure you got the software bulletproof. We want to do binary to decimal conversion. How's that work? Well, basically, you take an input and you simply just do a modulo by 10. Right, modulo 10. So if the input is 5,678 modulo 10, you get 8. Modulo gives you the right digit, right? Rightmost digit, least significant digit. And then you divide by 10, which drops the least significant digit, right, and it rounds down. And then you just repeat the process. So what you end up with is every time you do a modulo 10, you get each digit in order from right to left. That's it. That's really all there is to it. Pretty simple. However, you might be thinking, wait a second, we don't have an instruction that does modulo. In fact, a lot of CPUs don't have a modulo instruction, right? So how do you do modulo? Modulo, of course, is the remainder after you divide. So how do you do that? I don't know if you can subtract. Maybe. The way I came up with it, I was proud of myself when I figured this out, so we take advantage, remember that multiply h instruction? You might have been wondering like, okay, how often are we going to use the multiply h instruction? When is this going to become relevant? Well, I came up with this idea where you can use fixed point multiply in order to perform a divide. So basically, you take if you could multiply by 0.1, that's the same as dividing by 10, right? So you can take 0.1 and you can represent it in binary as a fixed point number, right? Remember, fixed point. Now the problem, though, is that here's the problem. 0.1 actually is not a is it rational number? So 0.1 in decimal is 1/10. It's a rational number. It can be represented by a fraction. But in binary, it can't. You would need an infinite number of digits to represent 0.1 in binary. Because remember, in binary, you have to add up powers of 2. You can't add up powers of 2 and get 0.1, right? So obviously, your 0.1 is going to be an approximated 0.1, right? Right. Now, because it's approximated, you want as many bits as you can get. So if you have 32 bits in your registers, you want to put 0.1. I need to have every one of those bits to be a fractional bit. Okay, that way I'm going to get as close as I can to approximate 0.1. How close do you get? I don't know. It's like within 2 to the negative 32nd power, basically, right? Which is 1/4 billionth. That's as close as you can get. That's pretty close, though, right? But yes.
Are you talking about representation when we have like some fixed point and then after it's 2 to minus 1, 2 to minus 2, and so on, or if you are talking about floating point representation?
No, fixed point. So we're in fixed point. So the idea is, I don't know if you guys did this in your 212 class, but so you have 0.1, right? And you want to do binary. So the way you do it is you double it, right? You can do 0.2. And because when you doubled it, there's no non-fractional digits there. You put a 0, right? And you double it again, 0.4, right? And again, it's 0.4, so that's a 0. Then you double it again, and you get 0.8, and that's a 0, right? But then you double it, and you get 1.6, so you can put a 1 there. You drop that 1, and then you take the 0.6 and double it, you get 1.2, and again, there's a 1 there. So then you drop the 1, and then it becomes 0.4, 0.8, right? and then 1.6. And now you can see there's a repetition going on here, right? So 0.1 in base 10 is going to equal point, and you read it from the top down. So 0, 0, 0, 1, 1, and then 0, 0, 1, 0, 0, 1, right? But then it starts to repeat, so that was from the 1, yeah, so 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1. That just repeats forever. Sorry, 2 zeros. Yeah, so it's always 2 zeros and 1, 2 ones, 1, 1. Yeah, and on and on and on. It goes forever, right? So in 32 bits, you would just be taking the first 32 of these, which I might already have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 20. Yeah, I've got about 32 bits there, approximately, right? So that's basically 0.1, but it's non-rational, so it goes forever. But you can get within your precision. You can get within 2 to the negative 32nd power. So anyway, so my point is that you take all 32 bits and you make that 0.1. And then you multiply that against your number, your input, like this, right? Which is all non-fractional bits, right? So if you take a 32-bit number with 0 fractional bits and you multiply it against another 32-bit value with 32 fractional bits, your result is a 64-bit number with 32 fractional bits, which is great because then that means the multiply H instruction will automatically give you for free the non-fractional bits of the product, which in this case is going to be this part, right? So that's the divide round down, right? Now, how do you do the modulo? Well, the modulo is a little bit more complicated because if I take this number and I multiply by 0.1, then I'm going to get 0.8. But now it's 0.8 is now in the lower 32 bits of the product, right? So how do I convert that back to just a regular number? Well, it's easy. I do another fixed point multiply. I take the 0.8, which is now 32 bits, 32 fractional, multiply that by 10, no fractional, and if I do that with a multiply H, I will then recover the 8, or at least I should. There's going to be some rounding error in there, though, because the 0.1 is not exactly 0.1, right? But I should recover the 8. So in other words, what I'm saying is that all you have to do is you multiply by 0.1. So first of all, you have to have, let me back up here again for a second. You have to have two constants chambered, ready to go. You got to have 10 and 0.1. Those are your two constants. So you take the input value from the switches. User puts the switches up. That gives you a binary number. Multiply it by 0.1, which is basically just 2 to the 32nd power divided by 10, by the way. 2 to the 32nd power is about 4.2 billion. So if you look at 0.1 is 429,000 something, right, in decimal. That's really what 0.1 is in that fixed point. So you multiply by 0.1, and that's going to give you 23.4. Now the 23 is already, you got it. It's the multiply high gives you the 23 right off the bat. So you don't have to do anything. The 0.4, though, needs a little post-processing, right? Because 0.4, what's 0.4 in decimal? Unclear. So you multiply that by 10, and that'll recover the 4, right? So basically what I'm saying is you really just have to do, a multiply H and a multiply when you do the 0.1, right? Because you got to get the upper and the lower half of that. So you have to do 2 multiplies when you do this step. But then when you do this step, it's just multiply high. So in total, for every digit, there's 3 multiply instructions, 2 of which are multiply highs and 1 is just a regular multiply. Yes?
We discarding 23 out of 23.4 by just having a bit mask, or how we do that?
Oh no, the 23, no, you don't need a bit mask. That's the multiply H. So when you do the multiply H, the result of the multiply h you can use to overwrite the original value, right? So basically the step is you use a CSSRW instruction to read the switch values into, like, say, register 1, right? Then you multiply that register 1 by the 0.1, right? And you put the result in register 2. That gives you the 0.4. Then you multiply high by 0.1, again by 0.1, and you can overwrite register 1. So you can blow away.
You talking that multiply high gives you things which are after decimal point and just multiply
Right.
which is before.
Yes. Left of the multiply high gives you the left of the decimal point. Multiply gives you the right of the decimal point. So multiply high is going to give you the integral part of the product. Multiply is going to give you the fractional part. But the fractional part is not useful until you then multiply it by 10. So in essence, you're doing a modulo, because you divide by multiplying by 0.1, and you get the modulo by taking the product of having multiplied by 0.1 and then multiplying that by 10 to recover the remainder from the divide by 10. So that was the way we came up with this. Now, again, though, that's a little, there is some rounding error. It's not a real divide, and it's not a real modulo. It's a fake modulo because of the fact that we're approximating with fixed point. But I've never seen a case where the numbers have come out wrong. Yes?
But if we have divide and subtract instruction, can we just get the number, divide it by 10, and then from original part subtract the result of this division? And what you will end up with is a reminder.
Oh, yeah, sure, you could do that. You could do it that way, too. I think that would be more steps, though. But, yeah, you could do that. Maybe not. It would still be another multiply. Yeah. Yeah, you could do that. You could do it that way if you want to. I don't mind. That's fine with me. Okay, okay, so now, let's see. Okay, got some little bit more time here. Okay, so that'll be the second. So the objective, and we'll give you a lab sheet for the next, we gave you have it. It's on Moodle. The lab sheet says that you have to write a program and then deploy that with your hardware on the DE2 to create this converter. So the objective is you'll flip the switches on the DE2 board and you'll have the decimal value. Yeah, the decimal value. So remember, you guys did a 7-segment decoder that produces a value from 0 to F. Well, once you implement this this program, you won't get A to F anymore. You'll just get, every digit will just be 0 to 9 because it will be base 10, right? So your 7-segment decoders will, never get to exercise all 16 possible outputs after you write that program, when you run that program. Okay, so let's switch gears here and go back to branch instructions. This will be the next lab. You don't have to do branch instructions in lab 3. This is lab 4, but I want to get started on the lecturing on this. 1, so I can cover this stuff in the exam, and 2, so we can get this out of the way. So you guys will have the information you need for the lab for the rest of the semester. Okay, so the branch offset is the immediate field. Now, the immediate field is really goofy with branches. You might say, wait a minute, with MIPS it was just the immediate field, is the upper 16 bits of the instruction. Yeah, not so much with RISC-V. RISC-V has a crazy immediate field for branches and jumps. I'll get to that in a minute. But there is an immediate field with B-type instructions, and it's the branch offset. What's that? Just pretty much like if you don't do a branch, you just increment the PC by 1. You execute instructions in the order they're in your program. If you get a branch, and if the branch is taken, you don't go to the next instruction. You add something other than 1 to the PC, basically, and that's the offset. It just tells you how many instructions to skip if the branch is taken. Now that value can be positive or negative. So if it's negative, you go backwards in your code. If it's positive, you go forward in your code. If it's a loop, obviously you're going backwards because you're going to loop, 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 get to the end, go back up, get to the end, go back up, get to the end, go back up. If it's an if statement, you go forward. You skip stuff that would be in the part of the code you don't want to execute because of the if statement. Yes?
If you go from the some point to the exit, from the loop to the exit, while something...
Yeah, if you have a break, that's right. If you have a break statement in your loop, yeah. A break will cause you to jump down, yeah. Yeah, but when you actually iterate, you go back up. So yeah, so that's the immediate field. So hopefully you guys remember that that was the same way that it worked in MIPS. It's called PC relative addressing, right? Okay, well there is a catch, and this used to annoy the heck out of me when I was in grad school because people describe this in different ways. The whole idea of PC relative addressing is you take the program counter, you add the offset from the instruction, which is the immediate, and that's where you're going to go. The problem is, what is the PC? What are you considering to be the PC? PC, of course, being the program counter. It's supposed to be the address of the instruction, but which instruction? Is it the address of the branch instruction that we're talking about, or is it the instruction of the next instruction that's currently being fetched, which is the value, the instruction after the branch? Sometimes they call that PC plus 4, right? Well, now you might say, why is that important? Well, it changes the way you calculate branch targets, right? In other words, if you wanted to do something like really bad and you wanted to have a branch that branches to itself, for instance, right? That would be an automatic infinite loop that you could never get out of. How do you do that? Well, if the branch is calculated relative to the next instruction, then your offset should be -1. But if the branch is calculated according to the current branch instruction, then your offset should be 0, right? Assuming, of course, that you're trying to branch to yourself, right? So which was it? Well, I don't know. Who knows? The way you figure this out is you write a code, you write an instruction that branches to itself, and you check to see how it was assembled, basically, right? Because how are you going to do it? It's always unclear when you read the instruction set architecture. It's like, which PC are they talking about? So this screenshot is from RARS, and this one's from MARS, right? And I wrote the same instruction, branch if equal T1, T2 to foo, and foo is a label on the same branch instruction, right? Okay, so this is the assembly instruction, and then this is the machine instruction, right? Notice the difference. In RISC, RARS, the offset is 0, but in MARS, it's -1, right? So obviously, there's a difference in how they calculate the targets, and in RISC-V, the targets are calculated relative to the actual branch instruction itself, right? So in other words, if your offset is 1, that means you go to the next instruction whether you take the branch or not, right? If your offset is 0 and you take the branch, then you're done. You're stuck forever, branching to yourself, right? So in your code, what is the implications of this in your code? In your code, remember I mentioned that you've got a PC fetch over here, right? You got this. Oh, I don't show it here. I don't show it in these ones. Where's the PC? Yeah. So we got PC fetch. So PC fetch is fetching the next instruction, right? So you don't want to use PC fetch. You want to use PCEX. And you might say, well, you don't show a PCEX. Well, yeah, I don't. It's easy. You just put a register, put the PC fetch in one end, and PCEX will come out the other end, because the register just delays for one cycle, right? So you delay PC fetch to get PCEX, and then you'll have two PCs. One is the instruction next that it's being fetched, next in your code, and the other one is the current instruction address. Yeah, that's so. Now you might say, now if you were doing MIPS, you would use PC fetch. In fact, that's what we did with MIPS, but now we have to use PCEX, just because of the crazy RISC. I don't know why they changed that. In fact, I thought it was the MIPS guys that came up with that PC plus 4 idea originally, but so yeah, so that's the difference. Okay, so now let's talk about here the immediate field. So this is, yes?
So if we in assembly language have labels, we just substitute in French instruction labels with the instruction? Yeah,
no, so that's, okay, so that's a good question. So in assembly language, you don't have to worry about that offset at all. Because, like for example here, I just wrote foo as a label. I didn't have to worry about this, right? The only time you have to worry about this is if you're designing hardware. Even as an assembly language programmer, no one cares. That's why no one makes a big deal out of this. Like in 2.12, no one really talks about this much because it only comes up if you're actually designing the physical data path for calculating the branch target. And they do address that a bit in the textbook, but it's not a big deal. In this class, it's a big deal because it's going to make the difference between your branch instructions working or not, because we're getting the code from RARs. So you have to be simpatico with RARs when you design your hardware. Otherwise, if you write the code with RARs and you run it on your CPU that calculates it this way, it doesn't work. So it's important that you notice that. But yeah, that's the only reason it's a big deal. But yeah, you would never use, now you can use a target actually in RARs. You could put a number here and say 1, in which case that 1 would go directly here. No one does that though, they use labels. So it's only a hardware thing, this offset thing. Okay, so the branch instruction uses the B type. And this is, in my opinion, this is pretty awful. It's the way they did this. I cannot imagine, I don't understand, I don't know why they did this. Okay, so first of all, there's 2 immediate fields. One of them is in the upper 12 bits? 10 down, no, 10 down to 5 is 6 bits. Yeah, and then that's 7. So yeah, there's 7 bits there. I think that lines up with the func 7, doesn't it? Is that the func 7 field? I think it is. Yeah, I think it's pretty much just, yeah. Func 7, yeah, 31 to 25, that's right. Okay, so what the func 7 field normally, or used to be used for, we're now going to use it for part of the branch offset, right? So we're going to have 7 bits of the branch offset. Now obviously 7 bits is that's not going to give you much branching ability, right? It's only going to give you the ability to go forward or back 64 instructions. Or forward 63, back 64, because it's 2's complement. However, it also has some more bits down here in the bits, I forget which bits those are. I should have labeled this. Oh, well, this is opcode is 7 bits, so this would be 7 up to 4, 5, so 7 plus 5, 12 minus 1, 11 down to 7, I guess. Yeah, 11 down to 7. These bits. So that's 5 bits. So that would have been a register field, right? Was that the RD field, I think? Before? I forget. This is the thing that's always confused. Anyway, 2 immediate fields. One of them is in the old RD field, one of them in the old func 7 field. But they're not even concatenated together because this one is bit. Okay, so the immediate is bits 12 down to 1. Okay? Now you might say, why is there no bit 0? Okay, bit 0, this is so confusing. So they don't have bit 0 because they assume bit 0 is 0, which means that the immediate is always a multiple of 2, right? But it represents a byte address, so it really should be a multiple of 4 because instructions are 32 bits, right? That's how it is in MIPS, 32 bits. But remember I mentioned earlier this today, there's a 16-bit version of the RISC-V instruction set. So the reason they have the ability to do 16-bit addresses with the immediate field here is to support that. But in this class and in RARs, unless you put RARs in 16-bit mode, immediate 1, which is this bit, will always be 0 because it's going to be a multiple of 4. You guys with me?
Yes.
So that's confusing, but also the bits are scrambled. So
Why?
I don't know why they did that. It's crazy. But luckily, I figured all this stuff out for you guys, and I'm going to give you the code for it, so you don't have to worry about trying to reassemble this thing. But basically, it's bits 12 down to 1. So bit 12 is up in the bit 31 of the instruction. Then you go down and you pick up bit 11 down here in this part of the instruction, which is bit 7. And then you pick up bits 10 down to 5 up here, which is bits 31 32 down to something. And then you go back down here and get the rest of the 4 bits. So this table gives you which instruction bits map into the offset bits. And this table does the same thing, except this one is sorted by the instruction bits, and this one is sorted by the offset bits. So if you're going to try to calculate the offset, the first bit is instruction bit 31, the next bit is instruction bit 7, then the next 6 bits are instructions bits 30 down to 25, and then the last 4 bits are instruction bits 11 down to 8, and then you add a 0, and then you delete 2 bits from the right side to make it divisible by 4, to divide by 4, because our instruction memory is word addressed. So in order to do all that, luckily with bit twiddling in system Verilog, it's very simple to actually do that. In Verilog, you just write the following code. You say assign branch offset EX, and it's EX because it's instruction EX, and this is combinational logic. Basically, you just take bit 31, concatenate it with bit 7, concatenate that with 30 down to 25, concatenate that with 11 down to 8, and then add a 0. And then the branch address EX, so this is the offset, the actual target address you're branching to is going to be the PC EX, as I described why it's EX. And then you add the branch offset, but you delete bits 1 down to 0 to divide it by 4, because your instruction memory is word address. Now you might say, wait a second, hold on. Why did you duplicate bit 12 in there though? Why is there 2 bit 12s? The reason I did that is because your program counter is 12 bits. It doesn't have to be 12 bits, but we just wanted everyone to be consistent. 4K by 32 instruction memory. Okay? But we wanted this to be 12 bits too. So we took the sign bit, which is branch offset 12, and we added an extra one. So we assign extended it, because this part of the branch offset is only 11 bits. So we add a 12th bit here, and so this way we can add 12 bits plus 12 bits. You might say, well, wait a minute, is Verilog going to freak out if you add 12 bits to 11 bits? No, but I think Verilog will 0 extend. So I think if you don't do this, you won't be able to branch backwards. It'll kill your sign bit, which would be a bug. That would break, like your branches would no longer have the ability to, you wouldn't be able to build a loop, basically, right? So that's why we did the 2 12, that's why we did that. So I'm sorry that's confusing, that's why we just gave you the code. But yeah, that's RISC, that's one of the things about RISC-V I don't like. Yes?
Could you, instead of in this sign statement and the last, previous to the last one, like instruction X 11 to 8, 1 be 0, instead of this, just do instruction X 11 to 7, since you still delete the second bit, and then use this add, but just duplicate like 2 times branch offset 12.
Yeah, you could do that. Yeah, the suggestion is just pick up a bit from the opcode, and because you're going to clobber it anyway when you get to this line. Yeah, that'll work. Yeah, that's fine. Either way, that's another way to do it. Okay, jump instruction now. That's the J type. This one is even weirder, if that were possible. So this one has this one uses essentially the U type format. Remember the load up immediate? It's got a 20-bit immediate, but it's actually a different format. It's J type. You might say, why do they call it J type? It's the same thing as U type. Yeah, it is, but the way you interpret this is different. It's the same format as U type, but the bits are interpreted differently. And boy, is it weird. Again, everything is basically scrambled. Yes?
Why to divide into types of instruction? Why you all have G and U type if you can't just have one type for both?
I don't know. That's a good question. Yes?
The only theory I could only think of that that the reason why they would do that was to make it just different enough so that they would not get a copyright strike from Mars.
Yeah, it's
That is
possible. From MIPS, yeah.
Yeah, that is the only reason why they would obfuscate
Yeah.
this much.
You know, the ironic part about that, though, is that MIPS, after RISC-V came out, MIPS basically became free. But you're right. Before that, they would have been sued if they were too similar. But now the point is moot. Although it's still, there may be some catches there to use it. May not, you may still have to license it and just not pay. I don't know how that works. But anyway, okay. So I'm out of time. So we'll pick this up after the exam. Okay. So we'll see you next time.